Evening, everyone. I hope everyone can hear us, see us well. We're going to give it another maybe a minute or two before we kick off it properly. But just a couple words, just of introduction. My name is David. Not actually Michelle Smith, as it says on the screen. I will mute everyone. Maybe it'll be easier for now. I work for IO Associates, and I specialize in recruiting Java professionals across London. With us is my colleague Mason, who's also recruiting Java professionals in London on the contract side. And today we're going to have a talk from Erik. I'm going to pass it over to Erik now for him to introduce himself as well.
Yeah, thank you, David. My name is Erik. I'm a director at Hivemind Technologies, and we're very glad and happy for the opportunity to talk about Kafka, which is one of our core technologies today. We've been using it for quite a long time across all our projects. And I think we've noticed a lot of interest for this technology in the last couple of months, especially like with customers adopting cloud strategies and microservices. And Kafka is becoming increasingly the de facto standard for message-driven use cases. So without much further ado, I'll start my presentation.
Can we just say the format will be, I think Erik mentioned, we're going to split it into two. So 20-minute session or so, and then we're going to do break for a question and answers. And then we're going to carry on with another, 20 to half-hour session. And then we allow some time for question and answers in the meantime without any interruptions in between. Okay?
Fantastic. Thank you, David.
Perfect.
So, there we go. All right. Can everyone see my screen?
Yes.
Thank you. All right. So today we'll be talking about Apache Kafka, the message routing technology, not the author, and Kafka Streams, which is essentially the companion streaming framework for Apache Kafka. But before we start, I'd like to spend a couple of minutes about Hivemind, who we are. We're a remote-only company based in Europe with offices in the UK and Germany, with clients in those countries. Remote-only means that everyone at Hivemind is basically working from wherever he lives or she lives. And that is, we have people in 5 different countries and 3 different time zones across Europe. We speak Spanish, English, German, French. We're quite diverse group of people. And that diversity we also bring in our solutions and in our technical focus. What we usually do is build data platforms, cloud infrastructures, and microservices in cloud environments with a strong focus on the DevOps mindset. Just as a quick reminder, DevOps is not a role, it's a mindset. It's how you actually embrace and organize your software development practices and approaches. We are also advocates of extreme programming, and we organize ourselves with new work principles, which is basically a set of guidelines how to organize and self-empower teams in their work. So that's us, Hivemind. Today, we have basically 2 blocks in this presentation. We'll be talking about the Kafka broker. After that bit, we'll do a Q&A, as David just mentioned, and then we'll move on to Kafka Streams, the companion technology to Apache Kafka. So what is Kafka? So as it says, it's essentially a message brokering technology. Many of you will know message brokering in the sense of like message queues, like maybe ActiveMQ or MQ series or other proprietary products that are very popular in enterprise systems. But Kafka is slightly different from its provenance. It is not essentially a vendor developed system. It was born out of the necessity at LinkedIn to have a massive asynchronous message brokering system, a message log. At some point, they realized that this is so useful that they open sourced it in 2011. It became a top level project at Apache in 2012. And the people that maintained Apache at LinkedIn eventually left LinkedIn and formed a new company called Confluent. Most of you will have seen Confluent if you've ever followed the news around Kafka and the Kafka conferences. And that's essentially like the company that basically advocates and maintains primarily maintains the Kafka top level project. The main users are obviously LinkedIn, as always. It's a big, a very large scale Kafka user. You have Yahoo, Netflix, Spotify, and many other web scale companies use Kafka as their primary message brokering technology. And that has quite, there are quite some significant reasons around that, specifically in its architecture and how it differentiates from traditional or like, let's say, more common messaging systems, even the open source ones like RabbitMQ or ActiveMQ. So there are some significant differences in its architecture, and that is also the reason why web scale companies choose Kafka as their tool of choice. And that is because it is essentially designed for distribution and persistence across multiple nodes with replication in mind. So what you actually see is you run a cluster of, let's say, independent nodes that have an equal significance in the broker, in contrast to master-slave setups that you find in traditional architectures. And those brokers are coordinated by Zookeeper. Zookeeper is another popular directory and discovery technology that was introduced by Hadoop and is used by Zookeeper, by Kafka to coordinate and discover nodes in a cluster of brokers. Other than that, you have the concept of a publisher. A publisher is essentially an application that sends messages to those brokers. And the brokers take the message and persist those messages to disk in a log-based queue. And that principle of log-based queues are essentially the main differentiation factor behind the architecture of Kafka in comparison with traditional message queue systems. On the other side, like you have consumers, and consumers are essentially other applications that will request messages from other brokers using an offset length-based API. So that is essentially the three main actors in Kafka are these three. You have a broker that basically manages the queues. You have a publisher that publishes messages to that queue, and you have consumers on the other side that consumes those messages from that queue. Excuse me, press the wrong button. On the architecture side of things, as I mentioned earlier, this is not a typical master-slave setup, but everything is distributed. So producers are distributed, consumers are distributed, queues are distributed, and brokers are distributed. Messages are basically stored in that log with a TTL, a time to live. So essentially, messages can expire after a while. queues specifically are append only. So essentially every time you actually add a message to a queue, it is added at the end of that queue, as opposed to systems where you can introduce a record or replace a record or update a record within that queue. And consumers also have to maintain their own state. So they have to keep track of where they stopped consuming from the queue, as opposed to traditional systems that basically manage the state for the consumers. Throughput is achieved with two techniques, partitioning and replication. So partitioning, which is a concept that is also like popular in other persistent systems, you basically define a range of data and you store them in different machines, and you partition the data in different locations so you can consume independently from these different partitions. And
so can I just rectify the message are persistent with DTL? I think the time to live is defined at the topic level. You just said, okay, I want to save the message for this topic for 7 days, and that configuration is done at the topic level, not the message.
Yeah, that's correct. That's correct. Well,
there's no TTL at the message level.
That is correct. There is no TTL at the message level. That's correct.
Thank you.
But we'll get there in a minute when we actually look at topics. I just wanted to give a general introduction to the concepts. If you bear with me a bit, I'll explain how that actually works in the next slides. So coming back to throughput, so we have partitioning, the concept of partitioning. And in order to preserve and maintain durability, you have replication of these partitions. So if we look at the way the consumption looks like in a message broker, and this is essentially like a visualization of a topic, you can have an ordered log of messages 1 to 6. The architecture of Kafka is designed for concurrency. So essentially, there is no state machine that will guide or synchronize or introduce some locks. Consumers can independently consume from a topic without ever knowing anything about one another. So if you have like two different consumer groups and a consumer starts reading messages 0 to 4, that happens on his own time. And it is not disturbed by consumer B that is currently reading messages 1 to 3. And at the same time, a producer can continue to produce messages at the end of the topic without disturbing these consumers while they work. That is also a different aspect and a different approach to, let's say, relational database tables, where you always have a locking mechanism and snapshotting to ascertain that you have consistency in tables when write and read transactions happen concurrently. And that is the benefit of having a very simple pattern of just having an immutable log that only allows append operations. So you cannot change, generally you cannot change messages in situ. You have to append them. There is a special use case that we'll cover later for that kind of message compaction. But generally, if you just assume that a topic is, and you just know that a topic is generally append only and immutable, then that's the kind of underlying principle that we have in Kafka. So I talked about queues just to simplify the concept and to create a bit of, let's say, comparability with traditional queuing systems of the JMS kind. But there are no queues in Kafka. The queues are topics, or topics are queues if you want. So in Kafka, there's only that kind of message queue type. It's called a topic, and a topic is organized in partitions. And obviously, a topic can have multiple partitions, and these partitions are again replicated to multiple brokers. So the interesting bit about the partition is that is actually the underlying holder of the data set, right? A topic never actually really holds data. The partitions hold data. A topic is essentially an envelope around one or more partitions, and it shares specific configuration patterns, as mentioned by the person who just asked that question. So basically, you configure behavior of partitions on a topic level, and it is distributed across all the partitions of that topic. And if we look at individual partitions, if you look at the diagram there, you'll see that each partition has its individual offset. So an offset is basically a sequence number of a message in a partition. So if you start with a very empty partition, you'll have, and you have one, you start with an empty topic with one partition, you add a message, that message will have the offset 0 in that partition, and you add more messages and you increase the offset. If you then configure an additional partition, that partition will have its own sequence and will also start with 0, because essentially offsets are managed on a partition level. That makes it easy to keep track of the individual consumption of different partitions, but it also means that some partitions can be consumed faster than others. So it is not always the case that you'll have an even distribution of messages in all partitions of your topic, because that, again, is based on how producers publish those messages to those partitions and when the partitions were also created. So it's a common pattern of starting with a small number of partitions, and then if you want to increase throughput in the topic, you just add partitions later with different offsets and different, obviously also different amounts of messages that are held in that partition. So that's essentially, in a nutshell, like the basic fundamentals of topics and partitions. When we look at routing, right? So essentially how messages, when they are produced, how they're distributed onto partitions. Well, that's actually very simple. So a producer will send a message, and that message can have a key, right? So like, for instance, an entity ID or any kind of UID or whatever it is, it sends a key, and that key will be hashed and then used to route that message to a specific partition. So essentially, that ascertains that as long as you have like an even number of, you maintain the same number of partitions, when you actually produce a message with the same key, that message will go to the same partition, right? It's a very simple region mechanism. And essentially, if you like, it's like when you go to the passport office and you have multiple desks, and the desks are organized according to your last names. You always have to go. In my case, my name is Schmiegelow, so I always have to go to the S desk, right? And that's essentially how it works with message keys and partitions. Obviously, if they add more desks to introduce, because a lot of people will have S names, they'll introduce people with SA to SC, and then SD to whatever, and there's a new desk. If they change that, I'll have to go to a new desk, but I'm always routed according to my last name, like a message is routed according to its key by the brokers to the right partition. So that is a very simple distribution, but it's an important principle to know that can change also over time when you change the number of partitions in your topic. Now we have there's a special type of topic called compacted topic. And that one is actually really, really interesting because it allows folding of newer versions of the same message according to its key onto earlier versions. So instead of doing a cleanup just based on time, as we mentioned earlier, we have TTLs on messages, so time to lives. This special type of compaction will fold and delete messages according to the version of that message for that key. right? So let's say you have a compacted topic, and you have 5 entities, A, B, C, D, and E, and you produce A, B, C, D, E, and then at some point you want to publish an update for C. Well, that message is appended at the end of the topic, but the compaction process will remove the earlier version of C from the topic almost immediately, regardless of the TTL, because you have the compacted topic. You have that special type of compacted topic. So when you consume from that topic, you always get the newest version of those messages upon consumption. So this looks weird, but it has very, very significant benefits if you have a use case that fits the bill. So one classic example for compacted topic is the New York Times. The New York Times decided that they wanted to have a message, a topic, and a message-oriented storage for all articles they've ever written since 1845. So what they did was they set up a compacted topic, and they started obviously backloading all the older articles that they've published until then in chronological order with the right keys into their compacted topic. And now when they write new articles, they publish those articles to the compacted topic, and each newer version of the article supersedes the earlier one. So you can basically consume that topic in the right order with the right versions from that stream. The interesting bit is that compacted topic also never expires. So they don't have TTLs. And that's also something that you can do in Kafka. You do not have to configure like 7 days or 14 days or 21 days or whatever you want for TTLs. You can actually also say, I don't want my topics to ever expire. Of course, that has implications in terms of how much disk space you'll have to account for and how you actually plan your cluster and your resources for that cluster. But generally, it is feasible and not that uncommon of a use case, especially, let's say, in event source systems where Kafka is the event store. So that's compacted topics. It's quite interesting functionality of Kafka. It's often used in conjunction with deduplication. So basically, you have a system where you want to dedupe incoming messages from an unreliable upstream source. You basically define an input topic that is unordered, and you basically use the compacted topic for lookups and replacement of newer versions when they come from the upstream source. If we look at the Kafka consumers, we generally have 2 different types of consumers. The low level called simple consumer, which is kind of a misnomer because it is actually very powerful, also difficult to use, with fine-grained controls over message offsets and commits. And the consumer group API, which is like the standard way of using Kafka consumers, and also allows automatic offset management by Kafka and multiple consumption semantics. Going back to Kafka consumers, the multiple consumption semantics is actually a very interesting aspect of Kafka compared to also, again, traditional message brokering systems. Because in, let's say, traditional message brokering systems, when a message is consumed, it's consumed and it's generally popped out of the queue. So you can only consume it once, and that consumer is the sole holder of that message, unless you use topics, JMS topics, which are a bit like a broadcast functionality, which is sort of similar to Kafka, but not as powerful. And what makes the Kafka consumer or multiple consumption semantics powerful is that not only can you have multiple consumers of the same topic, but they can also share the state and coordinate consumption from different partitions. And you can also have multiple different consumer groups consuming from the topics for different use cases. So what that actually means is, let's say you have one topic of events. You have one application that wants to consume from that. Let's say a financial transaction processing application, and you have a topic that basically contains financial records with credit card transactions. That can use its own consumer group and consume those messages from that topic and do whatever it wants with that. And at the same time, you can have a bookkeeping system that will just keep track of all those transactions without interference from the other system. So you can manage consumption at the same time across the board from different applications without ever having to coordinate anything. That's a powerful thing, but that is also quite similar to let's say, JMS topics. You can have that as well with the broadcasting system. The interesting bit is what happens within a consumer group. So when you have a consumer group and you notice that throughput is an issue, right? You have, let's say, one consumer in one application. You want to scale that. So the way you do that is you add more consumers sharing the same consumer group ID. And each of these consumers will then divide the workload amongst themselves. And that is up to the amount of partitions that you have. So let's assume for a moment that you have a topic, and that topic has 4 partitions. And until now, you had one application consuming from all 4 partitions at the same time, like a standard use case, right? And you notice that throughput is suffering. Okay, so the next step would be to say, okay, I need some more power. So I'm going to add a second consumer, right? And you add that second consumer of that same application next to the initial one. And what then happens is that those 2 consumers will then share the workload of those 4 partitions. So each of them will then consume from 2 partitions each. Throughput is therefore technically doubled. And of course, it depends always on different runtime, on specific runtime characteristics, but let's say technically it would be feasible. And you can do that until you reach the same amount of partitions. So you could actually add 4 different consumers for those 4 partitions in that consumer group. You can't add a 5th, because that 5th will do nothing unless you basically add an additional partition to your topic. So that's a very relatively simple principle with consumer groups. It makes it actually very easy to reason about scaling and distribution in Kafka from a consumer side. So that's essentially like the basics of Kafka partitions and consumers. The interesting thing is that when Kafka was introduced, it was basically designed as an at least once message queue. So it would guarantee that you would get messages at least once, right? But it didn't have very strong consistency guarantees in terms of how often you'd get that same message. So deduplication, especially in cases of crashes or disconnects, were always, let's say, the responsibility of either the producer or the consumer, right? Because you basically cannot really, you can't be sure that, let's say you sent a message and then your application crashed, you didn't get the offset back, you didn't get an acknowledgement, but Kafka said it was fine. I took the message, I added it, and when you restart the application, you say, okay, I need to reproduce that message. Bang, you have the message twice. Same thing on the consumer side. Consumer message, you didn't have enough time to commit the offset, your application crashed, you restart, resume from the earlier offset, you consume that message twice. So that was essentially okay for all those web scale distribution and event management systems for a long time. But at some point, folks were saying, okay, we want to use Kafka also for like more heavy load use cases and more mission critical use cases like financial transactions. We need exactly once guarantees. And that's when Kafka introduced the transactions. Obviously, transactions are the way to go in relational databases if you want to ascertain that you basically commit your record to the database. So the transaction principle was quite evidently the way to go for Kafka. So in exactly one scenarios, producers and consumers must be aware of transactions and can only process records after operations are fully finalized. That's kind of obvious. So how does that actually work? So, excuse me. Okay. So in Kafka introduced the concept of a transaction coordinator, which is a piece of the Kafka broker system that basically manages transactions for producers. Producers have to identify themselves with a persistent transaction ID. So for instance, when you have an application crash, it will come back up and say, hey, by the way, I'm transaction producer XYZ. I just crashed. Here I am. I'm ready to work. So the transaction coordinator can actually recognize that producer, register that producer as a transaction emitter and an emitter of records. The transaction coordinator also stores transaction logs to maintain the state of a specific transaction, which is kind of obvious and also pretty much the way you actually design transactional aware systems also in other storages. And you have a whole phase of coordination with an init, essentially when the producer says, okay, here I am, I'm going to start emitting transactions. And then you basically prepare and identify the partitions where those records will go. Then you send the payload and you send a commit. And at the same time, the Kafka transaction coordinator manages the rights to the topics. The reason why this is basically done is that and that is different from the traditional producer who writes directly to topic scenario, is that the transaction coordinator lives on the cluster side and basically keeps track of the life cycle of a transaction. If the producer dies before committing, then that whole block of records that were committed in that transactions are marked as zombies, and they do live in the partitions and also visible in there, but they are basically recognizable as an aborted transaction. That is a very important principle because this gives us the ability to ascertain that we produce messages only exactly once, because they are only valid as long as these records have been committed properly in that transaction. Conversely, a consumer must also be aware of transactions because, as I just mentioned, aborted transactions are also in the partition, but they're basically marked as zombies, right? So if a consumer just consumes from that transaction, it will just get all those zombie transactions and think they're valid messages. But let's say it's a relatively simple thing that a consumer has to do. The only thing that it actually has to say is, by the way, I only want to consume read committed messages. It's an isolation level that you just configure, and that makes sure that the Kafka broker will only send messages that have a proper committed transaction to the consumer. So the principle of transactions is quite simple. It is very consistent and resembles very much the way transactions are managed in other storage systems, but essentially are quite easily implemented in the context of Kafka's uniquely robust and simple architecture. So lastly, when we look at use cases for Kafka, I mean, besides the obvious ones where we basically use Kafka as a metrics or log aggregation, we see that quite often still, that Kafka essentially is used to collect operational monitoring data or like sensor data and all of those like fast, small records. We did a few projects in that area as well. This is essentially an ideal use case because Kafka can allow in-stream aggregation and collect and update and aggregation of statistics for distributed applications, and while producing centralized feeds for, let's say, dashboards, etc. So metrics is a big use case. Then in event sourcing, Kafka is an excellent backend. And let's say if we look at microservice architectures that use event sourcing as a paradigm, Kafka is usually the weapon of choice to basically provide the asynchronous messaging muscle for that use case. And obviously stream processing, especially in big data, you'll find Spark, Flink, Akka, and all those stream processing frameworks that basically read from one topic, process it, and aggregates it or enriches it, and then produces it to another data feed. So those are like typical use cases that we see for Kafka, and are also the reason for its increasing popularity in a lot of different companies and organizations. So that's essentially the first bit of our presentation around Kafka. Before we start with Kafka Streams, I would like to give you the opportunity to ask questions around just Kafka and the Kafka broker.
It's got a question actually about log compact. How can you actually assure the order of the log compact itself, because it because you gonna want to compact some event with the same key. However, though event on Kafka itself, it only record on the public time. So if the public time is wrong, then the event gonna be in wrong order, isn't it? The application of it gonna be the log compact is not gonna be correlated version anymore.
Indeed. So compacted topics do not have, because you basically the position is different, do not have the kind of the timely ordering semantics that you would expect. That is also tied to let's say different ways of interacting with a topic. Especially we're going to look at a few of these in Kafka Streams as well. You can actually use with the Kafka API. You can actually also look at the representation of a compacted topic not as a stream but as a table, which makes it actually quite easy to interact with compacted topics.
Okay, nice. How about you know about the idea of like removing the Zookeeper actually? Because
Zookeeper is
recently
essentially on its way out. That's true. The reason why Zookeeper is still there is that it's still needed for like basic coordination of cluster nodes amongst themselves. Zookeeper used to be used for a lot of other things, including offset management of consumer groups. But all of that has now been moved to Kafka itself, especially with the introduction of Kafka Consumer of compacted topics. Like Kafka now has a very robust way of managing offsets. So Zookeeper is not necessary. The next version of Kafka the next major version of Kafka will do it with Zookeeper altogether, because they're going to use a different consensus mechanism for for broker-to-broker coordination.
Erik, how does I've always wondered, I've been aware of Kafka for many years, but I haven't really gotten around to learning it in depth. How does it deal with latency, the disk read and write latency? Because that's something that's always worried me. I've worked on some rather large big data systems for financial services, and writing to the disk was a big no-no, because that's really where you lose a lot of your throughput. How does Kafka get around that?
Oh, it actually has a very clever write-ahead mechanism. So essentially, brokers, especially the leaders of a partition, have the most recent regions of most recent sets of the records in memory. So essentially, every write operation is asynchronous, and you get extraordinarily impressive and quick responses from your broker network. And that is possible because we don't have master-slave coordination. You don't have locking mechanism at all, since everything is distributed and you always have one broker who is the leader for a specific partition. You can always ask that person, or that broker, for that data. So it makes it very easy and to scale across topics and partitions. However, obviously, running let's say a Kafka cluster on spinning disks on a VMware cluster on your old 486 box will not be much fun. So you definitely need machines with ample, let's say not much, but ample RAM, and you need fast SSD storage for your Kafka cluster.
Thanks.
Any other questions before we start with Kafka streams?
Yes,
I
quick.
see, sorry, I see Landy's raised his hand. That might be a question there, possibly.
Yes.
Double check.
I have another quick question if nobody else does.
Yeah.
Just wondering about you were talking about zombie records and transactions, and that led me to think about are those eventually compacted, or rather maybe a better question is, are compacted topics, are those messages ever actually deleted, or are they simply ignored? So is it in a virtual sense or literal sense that they're removed?
Oh, they're virtually ignored. No, they're literally ignored by transaction-aware consumers. That's why you have that.
But they still exist in the file, in the log file. They're never. So the log file is always immutable.
And that's an interesting bit, because and they will only let's say be compacted away once the TTL is reached. And that's one of the first question that I had in this talk was around TTLs and messages. And I'd like to come back to that question to answer it properly. TTLs are based on files within the Kafka data store. So Kafka stores bunches of messages in files on the file system, and basically calculates and compacts away those messages based on the file stamp of the file that contains the records. So let's say you have a bunch of like several thousand records in a file. That file has a timestamp of its last update before it basically rolled over to the next file. And the compaction process will just look at that file stamp and remove that file and all the transactions in it as soon as the retention time has been reached. Very, very simple mechanism, not very sophisticated, but bloody robust, because since Kafka does not have to look at messages individually, it doesn't have to bother with all the performance impact of let's say a message by message analysis like you would have in traditional let's say database storage systems, where you basically have to have a look at each individual record before you basically compact them away. The Cassandra,
so it's periodically moving to a new file. It's filling up a certain amount, moving to a new file, and then once the TTL completely expires for all the messages in the previous file, it just deletes the file.
Exactly, that's correct. There are some operational aspects to observe with that behavior, because obviously, like if you have a rebalance, so let's say a partition moves from one broker to the other, all those timestamps will be reset, because basically the new broker will be then the leader of that new partition, or you rebalance and reshuffle partitions across brokers, and that basically means that you also reset your TTLs, right? That's one thing that you, on the operational side, you'll have to keep in mind. And that can be a bit of a surprise for operators when they discover, hey, why the hell am I running out of disk? I have, this shouldn't happen because I have a TTL of 7 days or something. But in fact, when you have a rebalance of partitions to different brokers, you basically end up having 14 days of retention time, because obviously at the time of the rebalance, all those file stamps were basically reset to accommodate that partition on that new broker. So there are a few things that you have to keep in mind with that, but otherwise, the simplicity is also very robust, and it allows Kafka to deliver millions of messages a day on a single broker, single cluster, right? Which is much more difficult in traditional message brokering systems. All right.
Very cool.
I got a question. So when you have a group of clients connecting to a broker, how is it decided from where in a log start posting those messages, right? Because I probably don't want to start reading all the messages on a topic because they will be too old. But then what exactly is this trigger that decides when it is right, which one message is the first? Yeah.
That's actually quite simple. You have three different options. When you start consuming from an existing topic with lots of messages in it, and you have a new consumer group, right? The consumer group has an ID, it has a name. So Kafka will then basically create a new record for that consumer group. The consumer group can either say, I want to start consuming from offset X, if you know that, right? You can say that. That's the simplest option. You can say, I want to start from offset X for partition 1 and offset Y for partition 2, etc. If you don't know that, which is usually the case, you can either decide whether you want to consume from the earliest point of all those partitions or from the latest. You can configure that. That's essentially the behavior that you configure in your client. You say earliest, latest, like horizon, right? And then Kafka will deliver either the earliest message it has in storage, right? Or it will basically just give you whatever it has right now, right? When you start connecting, you say, I'm going to consume from partition 0, you just get the latest message. And then you start from there, and then your offset is calculated off that first initial message. But you can just configure that behavior in the consumer group.
Sorry, just a quick follow-up. So when you said the latest message, does it mean it will always be one message? It cannot be two messages from the partition, because then it's only one is.
No, it will be the latest that is just current in that point in time, right? So you basically connect to the partition, right? And whichever message has been produced at that same time is the first one you'll consume. And then every subsequent message as well. That also depends on the consumer configuration. Sometimes you say, I want to consume 10 messages at a time, 100 or 1,000 messages or whatever, and you have the poll intervals. You can configure all of that. But essentially, the message, the starting message for that horizon configuration setting is the message that was the latest at the point in time when you connected to that partition. That's how Kafka handles it.
Cool. I've got one more question, but if others people want to go.
Sorry, I've got a quick one. How does it decide how many partitions to create?
Oh, that's configured. When you create a topic, you say how many partitions you want to have. And if you don't specify the amount of partitions, it takes the server defaults, which is one.
Okay, but following on that, what's the best strategy? Because if you can define the right configuration, you have to define the right configuration of partition from the beginning of Kafka, because after all, it's difficult to reduce number of partitions.
No,
you can
it's not difficult, it's impossible. You cannot reduce the amount of partitions that you've got. The only other streaming system that can do that is Kinesis. Kinesis AWS, it's a very early fork of Kafka by AWS, and it has one cool feature, and that is that you can merge shards. Partitions are called shards in Kinesis. You can merge them, and that's actually kind of cool. But in Kafka, you cannot reduce the amount of partitions. If you do that, you have to create a new topic and replace it, and then migrate everything from one topic to the other.
You can increase it, isn't it? You can increase it.
You can increase it at any time. Yeah. That's not a problem at all.
One of the things you guys can actually look at PubSub Lite from Google. So recently they got a implementation of very similar like Kafka. They're using log as well, and then they actually apply order as well. But the number of partition is the automatic credit. So depend on the consumer, they're gonna create a number of partition for you. So you have no control of it. However, they can reduce and create it. Create more of it if they want it, so the performance gonna be quite high. You don't actually need to take care of it at all, and you don't need to achieve.
It's very simple. There's this old adage: where there's no competition, there's no market. So obviously, other companies will try to bring their own, let's say, take on the massive parallel message streaming problem to the market and try to promote that. There's even another project that tries to basically emulate Kafka on steroids called Pulsar, that has also interesting characteristics in terms of storage and distribution. However, the one major benefit of Kafka is it is ubiquitous. It does its job very well. It doesn't do its job perfectly. Of course, you'll find other message brokering systems that do specific things much better, like Kinesis, for instance, or Pulsar, or the Google thing. But the major advantage is that you'll find implementations for every single framework that you need, or from every single upstream or downstream source for Kafka, because it is basically the main project for web scale message distribution. And so the ecosystem consideration is actually an important one, and also the support that you get from Kafka. That's the reason why it is still, even after all those years, our weapon of choice. We've been using Kafka for the last 5 years now, and it served us well, right?
Yeah, I think the good thing about Kafka is about the offset as well. So they got the partition and offset, which basically you can actually go back to the to the front of the queue and read from there. If you got more control over the queue, you got, and normally with the other system, it is very difficult to actually go back to a certain point. If you actually you want to actually fix some mistake or something like that, it's very difficult to go back to the certain point. Because,
that's right. That's true. I'm a bit cognizant of the time, since we have a second section now. So if there are any other further questions around Kafka specifically, I would ask you to ask them at the end of the next section, along with obviously any questions that you might have about Kafka streams. So Kafka streams, as I mentioned, is essentially the companion framework for Kafka. So Kafka, Confluent, the company behind Apache Kafka, wanted to introduce a framework that would allow like manipulation of Kafka streams and processing of in-stream records as the base technology for all the other products that they have. So they introduced Kafka streams as an alternative to the traditional stream processing frameworks that existed at that time, like Storm, Apache Flink, or Spark, etc. So the interesting bit about Kafka streams is that it's extremely lightweight. It's just an add-on library. So it's not like a cluster, heavyweight cluster system where you basically say, okay, I need to run this this big cluster just for my streaming application, but I can just basically use it as a library within an existing application or microservice. It is like most stream processing frameworks, it is built on the simple concept of pipes and sinks. So you have a pipe with incoming data and a sink where it basically goes, and you have functional transformations in between. So the usual use case for Kafka streams is to run it in a Docker container as a JVM application. So Java, Scala, Kotlin, or Clojure, or any one of these will do. And you can just run it in a Docker container or in an existing application and just use the Kafka streams library to do your topic-to-topic stream processing. So why do you want to have another processing framework, right? So as I mentioned earlier, it's lightweight library. It's not like a cluster stream processing solution. So it's not really a replacement for Flink, Spark, and others, because all of these have specific implementation for other types of destinations. Kafka Stream is specifically designed to take an input from a topic and publish to one or multiple output topics. It's pretty lightweight. It has no other significant dependencies other than the Kafka, and it offers minimal latency, including run record at a time, like true stream-oriented processing. So it's essentially an ideal conversion and enrichment toolkit for topic-to-topic processing. Of course, you will always have arguments about, is Kafka Streams the right choice, or do you want to use something like Akka or other frameworks? But let's say in the canon of available lightweight processing frameworks, Kafka Streams is definitely something to consider. So how does that actually work? It basically runs as a process within your app. So if you have like an existing Java application, let's say, and you want to have one of the processes consume from a Kafka cluster, you can actually integrate that as a Kafka Streams implementation within the application. Usually, like we at Hivemind always suggest dissecting that and running that in separate services, but let's say you have that option. The interesting bit is that Kafka Streams also introduces the concept of threading, which is managed by Kafka Streams itself in coordination with the Kafka cluster. So what that actually means is that essentially a Kafka Streams application within, let's say, a single instance will then talk to the cluster, will find out how many partitions it can consume from, and will then create a topology of processors that is defined in that stream of Kafka, in the Kafka Streams application, right? Because Kafka Streams is specifically as a stream framework has a fluent syntax of transformations within the topic. So you start from a source topic, and you have different functions that can modify the records within that topic in the typical fluent syntax that we, like most of you are Java developers, so if you just think about the Java 8 Streams API, that's essentially like very similar to Kafka Streams. Even the different like functions have the same name, like a map, reduce, aggregate, etc. You'll find all of those names that you're familiar with in the Java 8 Streams API also within Kafka Streams, and which allows you to essentially do multiple transformations on the records before you emit them to an outgoing topic. So actually quite simple principle. And it also takes a big look at the way other functional collection modification frameworks work, and you can basically design your application around that semantics as a flow of transformations from one source to a sink, right? So that topology within that let's say application that you run it in will then determine the concurrency and the parallelism requirements of that topic. So essentially, what happens is, let's say you have like 4 different topics, and you start one instance of the application. Kafka Streams will then start 4 different threads to consume from these different partitions individually, and basically emit the output to your output topics. If you want to parallelize that, you can start new instances, and very similar to the way the consumer group API coordinates the workload, it will then distribute the workload to this new instance and start, instead of starting 4 threads in one application, it will then basically just start 2 threads, and let the other 2 threads run in the other instance of that application. So distribution is quite seamless and is managed by the Kafka cluster, which actually keeps track of the positions of the individual consumers within the Kafka Streams application. Conversely, it also keeps track of the producers on the other side. Kafka Streams is also transaction aware. So basically, when you use transactions and you want to have exactly once, you can configure that within your Kafka Streams application, and it will keep track of transactions and manage them for you within the stream and the flow of your topologies. Essentially, when you basically configure exactly once semantics, your Kafka Streams application will open the transaction, talk to the transaction coordinator, as mentioned earlier, commit the transaction at the end of the stream, and then go to the next message. Obviously, that has some implications because you have to make sure that everything before and behind is also transaction aware. So Kafka Streams has 2 different core concepts that are quite interesting. So there's a Streams one that we just talked about. So essentially, you consume records from a stream, and then you do functional modifications on them, quite simply, and then just emit those records one by one to an output topic. What we also have is tables. And tables are a really interesting concept in Kafka because it gives you the ability to look up and use an existing topic as if it were a table, and even perform basic SQL commands. There's a companion product called KSQL that allows you to do and execute SQL on a Kafka streams as if it were a Kafka topic, as if it were a table. So you can basically simultaneously change the view on a topic by either deciding you want to view the topic as a K-table and then do lookups and operations on that table, or you can basically consume the stream as the topic as a stream. So that makes it very flexible, and it's actually quite an interesting concept because it unlocks a lot of power to basically do, for instance, use cases like deduplication, where you have two different topics, and you want to make sure that when the records that you're consuming are not already existing in the outgoing topics, you can just basically use the K-table and look them up, and then decide whether you want to produce or discard that incoming topic. Makes it actually very fun to use as well. So what we also have in Kafka Streams is the differentiation between stateful and stateless transformations. Stateless transformations are quite simple. So those are all transformations on records that are basically only record oriented. So they basically don't have to do anything, not preserve state. They just transform that one record as it is, like map, filter, group by kind of operations, very simple things that run on the existing batch or the existing record in that stream. If you don't want to do more specific and more, let's say, advanced transformations that need to run on a collection of records or use sliding window operations, you need so-called stateful transformations. And that requires a store. And Kafka Streams then needs some kind of persistent store. It can be in memory or RocksDB instance, where it basically commits the state of the transformation for that specific instance that runs on that topic. And it allows then to use aggregation, count, reduce, and other operations that require state. In that, it becomes a bit more similar to those more heavyweight frameworks. But I think that the drawback of using a nimble, using a persistent store does not outweigh the advantages of using a nimble and lightweight library like Kafka Streams. Yeah, that's pretty much it. A quick introduction to Kafka Streams, keeping track and being aware of the time that we have. Do you have any questions around Kafka or Kafka Streams that you can ask?
Yeah, one question. Yeah. So, so we know that Kafka sits always behind the synchronous world of REST API microservice or MQTT mobile. So Kafka is a fire and forget. So it treats a batch of messages. There is no order guaranteed at the topic level. So there's an input topic. There's a batch treatment, and the result is put in an output or somewhere. My question is, when you have a REST or client server, you have a request waiting at the level of your Apache web server, how to correlate that synchronous world, the real world of mobile browser to server, to the asynchronous world? What's the best strategy?
Well, the thing is, that's a more, let's say, a more elaborate question, obviously, because there are some gaps between synchronous use cases and asynchronous use cases. So the best answer for that problem is a pattern called CQRS, Command Query Responsibility Segregation. So let's say in Command Query Responsibility Segregation, you basically say everything that changes a state of my entities is basically processed asynchronously as events. So let's say in your browser use case, let's say somebody wants to change his address, they'll basically type in their address, click submit. That is, let's say, a change set, a change event for that person's address. And it's processed by the command side of CQRS, goes to Kafka, is processed, and eventually is then submitted to the query side of things. And the query side of things is usually a read-optimized store that keeps track of the newest versions of those entities. So what happens is, instead of saying, look, I'm going to submit my change of address in my web browser, I'm going to send it off, right? And I'm going to wait in that session until the database says, yes, I've stored it, and here's the latest version, like you would do in a CRUD pass pattern, which is like the standard use case for like traditional applications that are backed by relational databases. You design your web application slightly differently. You just say, okay, I'm just going to publish that, and I'm going to say, I'm going to pull the read side of things until that appears, instead of waiting for the transaction to percolate and hit the back end, I'm just going to say, I'm not going to send an HTTP 200. I'm going to say send an HTTP 201, which says accepted. I've accepted your record. Please wait until it eventually gets processed by my asynchronous backend. And if you look at the big sites like Netflix or Spotify and all the others, they use these patterns to persist even the stuff that is displayed to users, just because they have to scale so much. That's the only way to ascertain that they have even distribution of resources and adequate performance. So obviously, when you start interacting with asynchronous and reactive patterns and use some asynchronous message broker systems such as Kafka, you also have to think slightly differently about how you actually design your front-end user-facing applications.
I think it's also about the session ID and the customer ID as well, isn't it? If you set it at a key, then it's gonna be go to a partition, and the event gonna be in order.
Yeah. Of course.
So at partition level, it's gonna be order.
Exactly.
So yeah. So I
have,
don't know why.
You have 2,100 requests, so you will have 2,000 partition, or
no. It is you only 2 or 4 partitions.
You need some correlation somewhere between your input streams and your output streams. And that key, if you put in your message, you need a component in the front of your Kafka that does the correlation between your request and your so that does the correlation between the asynchronous and synchronous work. You need a component that does that.
I would suggest, I strongly suggest to look at CQRS specifically. There's an excellent article by Martin Fowler online that actually explains the principles of that CQRS pattern clearly, and how you actually handle exactly that kind of use case.
Yeah, that's yeah.
That's actually quite independent from Kafka. It's just a design principle. That's how you basically say, okay, I'm going to send a command that has an entity, and how can I find and look up that entity elsewhere in that other, in the query side of things.
Yeah. For me, it should be over in order anyway, so it's not a problem much.
Yeah, exactly, because as you said, the ordering of the messages is consistent in the partition, right? Yeah. And it stays the same as long as you don't repartition. Obviously, if you repartition, the messages will be distributed differently, because the regions, the key regions, are then different across the partitions that you then have. Right?
Okay, thank you. Another question. So, you know that Kafka is this platform, streaming platform, but also it's a storage platform. You can store data on it. Yes. How about taking Kafka as your main storage rather than using relation database behind ScyllaDB or whatever? You pull all your data to Kafka. What is is it the right way to do it? Is it advantageous to just pull all your huge data to Kafka and use it as a streaming platform, also as a storage, definitive storage?
Yeah, let me answer that question, because like twofold. So generally, it is generally feasible to do that. You can definitely use Kafka as an event store, right? Perfectly fine. However, it is probably, in most cases, it's not the best way to store your data. For two reasons. First of all, storage is actually quite expensive. And if you have a high volume of messages, that kind of storage can be very costly, right? Especially because you basically have to configure your topics never to expire, right? They never expire, and your storage has to grow, and the only way to provide storage to Kafka is increasing the disks of the brokers. So that can be very expensive. That's why most of the time we at Hivemind we don't do that. We use let's say we offload the stuff in Kafka. At some point we just offload it to S3, right? Because S3 is an extremely cheap storage, and let's say older data is actually not that interesting. Nonetheless, the New York Times, as mentioned earlier, uses Kafka as their primary store for their articles, and they run well with it. But because they have a finite number of, like not a finite, but a limited amount of articles that they publish, it's really not that much, right? Maybe of like a few, in the 10,000s maybe, maybe a bit more, like let's say maybe 100,000, but nothing to write home about. We're not looking at millions of records. And that serves them well, specifically because they want to consume these articles in specific ranges. So the use case is well suited for using Kafka as a permanent storage. Conversely, in a lot of use cases, you do want to do lookups. And if you do big range lookups in Kafka, that can be actually quite slow. So that is not necessarily the best storage for the standard use cases. It has to be timely based, partitioned, and range oriented to make sense, and also have a limited amount of records that you're looking at to make sense as a central storage. Right?
I've got a question to ask, and it relates to one of the earlier slides you had, where you were inserting the message, and there were two brokers. So it might be, if you still can't roll back a few slides, where you have two brokers, and you were showing how message being persisted in one of the broker. And I was a little bit confused why, even though the brokers have this kind of what seems to be a replicated topic between different brokers, right? The message is only inserted into one of them. So what kind of was a little bit confused why there's only one error.
Trying to find, is this one?
Yeah, this one. Yeah. So I would expect the partition 0. So it's the same topic in both brokers, right? And the same partition 0, partition 0. Why arrow only points to one?
Yeah, okay, that's a good point. I'm happy to answer that question. So this way, in this scenario, and there's a bit of a problem with the labeling here. There's a label missing. So in this scenario, you have broker 1 and broker 2, and broker 1 of topic A is the leader for partition 0, right? So the message routing determined that message has to go to partition 0 on the leader for that partition, and that happens to be broker 1. So broker 2 is a follower of topic A for partition 0 and 1. So in this case, let's assume for a moment that somebody basically pulls a network cable out of broker 1, right? And broker 1 goes down. So what happens? The cluster will then send a rebalancing event leader election event, and will then ask all the brokers and all the replicas to basically report back their offset positions. And the best follower will then become the leader. So if that were to happen, the next message the producer would send for partition 0 would then go to broker 2, right? And then eventually broker 1 would come up, say, by the way, I'm back. Then the cluster would say, well, you know what? You're not leader anymore. You're now going to have to follow, right? And then broker 1 becomes a follower of broker 2. So that happens behind the scenes, and the only thing that might happen is that when leader elections happen, the producers are basically sent in a queue and have to wait until the leader election is completed. But it's super robust, and it's really cool actually, because you have that seamless like leader election rebalancing stuff that happens behind the scenes, and your consumers and producers can continuously consume and produce to the cluster, as long as you obviously have enough brokers.
So I guess in this case, what would be the next step after this arrow going to partition 0? well, it's asynchronous, so there will be no response back, but broker 1 will duplicate the data into other brokers.
No, basically what it does is it appends the record, right? And then it sends a sync event. And the leader, the follower of that partition will then say, okay, give me the latest batch of records. And then it consumes from that partition and receives those records and basically adds them to its own store. So that's how the replication happens.
It basically just becomes another consumer temporarily while it
Yeah,
syncs
it's
up
not
the
exactly
records.
a consumer because it uses different mechanisms. So it doesn't. It's not really a consumer, but basically there's a whole protocol thing within the broker. It basically says there's a synchronization event, and the broker pushes those new records to its followers, and then the followers have to say, "I'm following," and then they get the records. They're pushed down to from the leader to the followers.
Okay,
it is different from the consumption, but it's like a similar pattern if you want.
Can I ask a
they
question
mixing
about
the message actually?
Oh, sorry.
Sorry, is it on that scenario, can they miss some of the message when they actually change the leader?
Yes, that can happen. So essentially, there are some cases where it is extremely rare, right? But there are some cases where a broker crashes and received messages but did not replicate them to the followers. That can happen. But it's like, as I said, it's extremely rare.
I've got a question about transactions. Apologies if you covered this, because I had to step away for a second. So you have the two sort of styles of at least once and exactly once, and the second is for transactional delivery.
Yes.
How would that relate to, and this could be a dumb question, so apologies, but how would that relate to a transaction within the consumer, like a database? Like how would you ensure, I mean, is there like a distributed transaction, or how is that?
That's where the difference comes. That's where the difference where the significant difference between like databases and Kafka. Because like transactions are essentially markers on records. So interestingly enough, within a database, a transaction is only basically written to the snapshot, depending on the database technology, to the snapshot if the transaction was consumed properly and there's a lock on the table. So essentially you have the table, right? So when you start a transaction, the database locks the table and does not allow simultaneous writes on that table until the transaction either times out or is committed or is aborted. And once that happens, the data is written to the live snapshot of that table and the bin log and all the other stuff that comes with a relational database. In Kafka, that is not what happens. In Kafka, the messages are produced to the topic, but receive the marker once the commit marker once the transaction is committed. So they actually reside in the topic. They're written no matter what, but they either have a transaction marker or they don't, right? And so the only thing the consumer has to do is to filter out all the records that don't have committed transaction markers. And that's a significant difference. And the reason why Kafka does that is that it wants to avoid locking, right? Because Kafka is designed for throughput. So any kind of locking mechanism will harm throughput significantly. So that's why they do it with throughput and use a transaction log to monitor the life cycle of a transaction, and then basically commit the transaction marker, the write marker, to the partition in question.
Okay, so I mean, if I wanted to ensure that if I've got a consumer that wants to write off to its own database in a transaction, I can't see from what you described any way that you would kind of be able to coordinate the two different transactions, the Kafka transaction, the database transaction of the consumer, because they're basically independent things. Am I right in saying that?
The database, let's say if you can't sort of, on a consumer level, you can't do that because you basically just consume. That's correct. But what you can do is commit the offset only, and that's always been the case. Even like without transaction, you can still do that. So that's
what does that mean to say you commit the offset?
Yeah. So let me step back a bit.
Sure.
You can have sort of, if you have an application that just consumes from a Kafka stream, right, and writes to a different system, let's say a database or S3 or whatever, you can still have exactly one semantics without using Kafka transaction. And the way you do that is you manage offset commits on your end within the application. So you consume a batch of records, you write them off, and you only commit the offsets if that transaction was successful, right? And obviously you have to also implement rollback behavior if only the message were only partially committed, right? But you can actually achieve that on the consumer side with offset management. We actually do that quite often in with Spark applications at Hivemind, which is basically consume from event streams and write them to somewhere using Spark, and we just basically manage the offsets within Spark, and we only commit the offsets once the entire data frame or data set has been produced and written off to the destination
source. But I guess there's always the chance that you could get a failure just after you've written to the destination source and before you've committed the offsets, which would mean you'd end up getting them delivered twice.
That might happen, and that's why I earlier said that you basically also have to implement something that verifies that has happened and eventually rollbacks or compacts away them.
But that does mean though the consumer, in a sense, might get delivered twice in that case. Effectively, you'd still have to implement effectively support for idempotency and. Am I right?
Exactly. So it is, but it is very theoretical. To give you one of our clients is a financial institution, and they process 90 million records a day, right? And 90 million events a day. And we have, for the data lake infrastructure, we basically have an Apache Spark streaming job that consumes from Kafka and writes that off using that offset mechanism. And it's been running for a year and a half now. We didn't have a single instance of duplicate data because you can just basically rely on the cluster, on the Spark streaming cluster, to have that kind of level of durability and consistency before on commit of the offsets. It is technically possible that you don't have proper idempotency in such a case, but practically that doesn't happen.
And be careful, you're spiraling down a black hole of edge cases and corner cases. I've been down that route. You sit there and chase but what happens in this case? And it's true. Yeah. There's always a 0.0001 chance.
Yeah, absolutely. I mean, that's a fascinating bit about our jobs, right? So that we just basically, have those theoretical experiments, and we talk about this, even though it might not practically matter. It's still an interesting thing to think about, right?
Yeah, well, that is where it's really valuable, your experience, and David as well, yours, because in a sense, it's theoretically there, but does it really matter? Do you know what? Don't worry about it. I mean, you've just said 90 million, was it 90 million a day?
90 million records a day.
Times by however many days it's been running, and it's never happened. That's a pretty good statistic, isn't it?
That's a pretty good
thank you for that. Yeah, that's useful. Thank you.
All right.
Do we have any more questions for Erik?
No, that's it.
No?
Yeah, so I just want to say thank you everyone for coming again today. Really good talk. Thank you again, Erik. Really insightful. We've got a few things lined up for the new year, and we'll get all those invites sent out during the due course. If anyone has any topics that they'd like to hear about as well, please feel free to email myself or David as well. we're always open to ideas of what we can do and how we can do it better next time. We had over 60 people at one point, so really good turnout for this time of year. So just want to say thank you for everyone to coming again, guys, and then thank you, Erik, for that really good talk. I'm sure everyone's taken a lot away from that. So yeah, no, anyway, guys, thank you very much.
Thanks, guys.
We'll be in touch with the next invites over the new year.
Also, just wanted to add that you can always find recordings on our Meetup page if you ever miss anything, or if you ever want to go back to anything. There are always recordings of our Meetups.
Thank you.
Great stuff. Perfect. Thank you so much. Thank you so much, Erik, for doing the presentation.
Thanks for having me.
Thanks, Erik. Thanks, guys.
Thank you. Bye-bye.
Thank you very much.